Hello and welcome to the second part of Lecture 10 of EEE 23. We've discussed in the previous lecture the behavior of plane waves in a lossless medium. Now, what if we stumble upon a lossy medium? What is a lossy medium first? It's when our electric field and magnetic field induce a current within a medium, and then this medium disperses or eats up this electromagnetic propagation. So let's consider the case that the conductivity is not zero, or the medium is a conducting medium. So this is our Maxwell's equations, and our Ampere's law now has a conducting term, sigma E. If we solve for the characteristic equation of these two, we get this differential equation right here. So this is our this is our wave number or propagation constant. It becomes complex. So now we define a propagation constant that is complex valued. Okay? So this complex valued propagation constant right here is some gamma, which is the square root of, so this some gamma is equal to j times k, which is some alpha plus j beta, which is equal to the square root of this expression right here. So the result is that our differential equation actually becomes, no, it's not plus, it's actually minus gamma squared E. Okay. So what is the result of that differential equation? Before we go there, let's consider this equation here first. If you put that in a calculator, in a scientific calculator, you'll get a syntax error. How do you solve the square root of a complex number first? So first, you convert this complex number into its auxiliary form or its polar form. Okay? And getting the square root of this polar form, okay, getting the square root of that, just get the square root of the magnitude, and your phase will be divided by 2. That's how you get the square root of a complex number. Okay, so now what will happen to our field or our electromagnetic wave when we are in a lossy medium? So if you solve this differential equation right here, okay, so Laplacian of E minus gamma squared E, equal to 0. So let's consider the case then. Let's consider the case when we are propagating only in the z direction. That means our differential equation becomes this. So the second partial derivative of your electric field, which is only in the x direction, minus gamma squared multiplied to E times x equals 0. The solution for this differential equation is this. So we have an exponent that is complex. And if we convert this to the time domain, consider only the forward propagation for now. If we convert this to the time domain, then we have this term that is multiplied to our original expression. So remember that this cosine omega t minus beta z is the propagation This is due to the propagation. Okay? And the wave number of that propagation is now equal to beta. Okay? So this is the imaginary part of our propagation constant. This alpha, as you can see, this function, as you move along positive z, since this is forward propagating, if you move along positive z, this term actually dwindles. So it actually decays. So this function right here is responsible for the decay in our propagation. We call this the damping constant. Because of alpha, there is damping. So alpha is the damping constant, or more formally known as the attenuation constant. For a lossless medium, there is no attenuation, therefore alpha is 0. If we do the same analysis, we can verify that hy of z is equal to 1 over eta, where eta, remember, is your impedance, intrinsic impedance. But eta here is now, instead of omega mu over k, it becomes j omega mu over gamma. Okay? So it means that our impedance, okay, our impedance is complex. So where can you find a complex impedance? If we have a resistor that is in series with an inductor, or a resistor that is in series with a capacitor, or basically any combination of a resistor, inductor, and capacitor, which is present if we have a conducting medium, a resistance, capacitance, and an inductance. Okay, now consider the case that our traveling wave is in a good but imperfect conductor. So it's imperfect. We define the skin depth as this. Delta sub s equals 1 over the attenuation constant, which is the square root of 2 over omega mu sigma meters. So this is the depth into a conductor in which the magnitude of the fields decay by an amount of 1 over e, or 36.8%. So if, let's say, our wave enters a boundary that is conducting, okay? So it enters a boundary that is conducting. This conducting surface will have currents that will disperse, okay? This electric field will induce currents in our conducting region, and then the traveling electromagnetic wave actually decays as it goes inside the conductor. And at some point, very far into the conductor, there will be no more wave. Okay? So, the skin depth is the thickness of the conductor. Okay? The thickness of the conductor that will make our electric field decay by, our electromagnetic wave rather, decay by 36.8%. Okay, so if we apply that if we power up our circuit with a very low frequency, okay, so you can see here that it's dependent on frequency. A very low frequency, it means omega is very small. This skin depth is very large. That means almost all of our field actually penetrates inside the conductor. So it goes inside. But if we have a very fast excitation, so very high omega, this delta S is actually very small. Therefore, the penetration of our field can only go so far, and it will disappear at some point. Okay? So this is called the skin effect. If we go higher in frequency, the wires actually have more resistance. Why? Because the currents only choose to be nearer the skin of our conductor or nearer the surface of the conductor. Because of the very fast electric field or very fast excitation, or very fast everything, the current will only be placed nearer to the surface. Effectively, some chunk of the conductor is not utilized by the electrons. The effective resistance of our material actually increases. So recall that the resistance is equal to uh, L over sigma times A. Due to the skin effect, assuming our conductors have the same length, the skin effect effectively reduces the area at which the currents flow. Therefore, A is smaller, R is larger. So if you're working with very high frequencies, you have to consider the thickness or every physical aspect of your system. If you want to know more how to do high frequency engineering, you can take a higher course, maybe EE 217 or ECE 157. Right? And consider all of these into our design when we are designing high frequency circuits. All right. So that is all for the lossy medium. So as you've noticed here, it seems that our magnetic field here and our electric field here is a complex valued electric and magnetic field. So the fields are complex? That's a question mark. Complex fields. There's an imaginary component. There's an imaginary field. Okay? It's not really imaginary. All right? It actually represents the phase at a certain point. So the actual electric field needs to be converted first to time domain so you can get your actual expression right here. So the electric field at this point, let's say some point xy or whatnot, xyz, the electric field value is ER plus JEI. That means that the electric field initially at time t is equal to 0 has a phase of some phase that is the phase of this. It means that if it's phase 0 at time t is equal to 0, then it is at a maximum. At time, sorry, if the phase is 90 degrees, purely imaginary, at time t is equal to 0, then initially it has a 0 electric field. Right? And because it changes with time, so at some point the value of the electric field at that point becomes maximum, and at some point the value of the electric field becomes minimum. The actual function of that point in space with time is just get the real component of this and you'll get this expression for the electric field. Right. So now how do we propagate? Okay. How do we generalize the propagation of our electromagnetic field? Sorry, electromagnetic wave rather. How do we generalize the propagation? What if we have a current in that region? What if we have charges in that region, etc., etc.? What if we have a conductor in that region? Right. So we actually characterize the propagation based on how much power enters and leaves the region. Okay? We want to know how much power flows when there is an electromagnetic propagation. And that is defined by Poynting's theorem. So, if I remember, for Physics 72, Poynting's theorem is only pertains to this function right here. Okay? So, this E cross H points to the direction of propagation. But the actual Poynting's theorem actually sums up all of the power flow in any generalized space. So Poynting's theorem has 4 components right here. If you want, the proof for this can be found in our reference book, Height. So I won't go over the proof. All right. So let's just do the math, or let's just interpret the math. This integral right here is a closed surface integral. This is the power going inside a closed surface. So the power going in, so we have some closed surface right here. There's power, or there's field going inside the closed surface in any direction. Okay? Take note, any direction. Okay. This first term, the integral of j dot e dv, is the power dissipation due to a current inside the region. If there's current inside the region, power is being consumed by that current. Okay? Okay. So this term right here is the total energy stored in the electric field. If there is an electric field in this region, right, there's electric field in this region, the total energy stored by the electric field is 1/2 d dot e dv. This should look familiar to you. This is the energy stored in an electric field. And finally, here, this is the total energy stored due to a magnetic field. Okay? Thus, if this is the power flowing in, the power flowing out is just equal to the positive of this, the closed loop integral of E cross H dot ds. So just note, since this is a cross product, so the power flowing out that is perpendicular to the surface of a closed surface, the power flow is actually perpendicular to also to your electric field and your magnetic field. And this is called the Poynting vector S. So the Poynting vector pertains to the direction where power is flowing out. Okay? So how do you interpret that? The closed region is something like this. Any closed region has a resistance that dissipates the power, some capacitance that stores electric field, and some inductance that stores magnetic field. Does this look familiar? It should look familiar. It's your RLC circuit. Okay? Sorry. Let me just try to draw it. And there you go. So your resistance dissipates power, your inductance stores power in terms of its magnetic field, and your capacitance stores power in terms of its electric field. Okay? So we're not really concerned with the power. We're concerned more with the time averaged power. Since this is a sinusoidal in time, the power also varies with time. And the interesting part here is the average case. Actually, the average power inside a region, or going into a region or out of the region, is just equal to 1/2 the real part of the Poynting vector. So you have to take the conjugate first of this HS. So what does it mean when we say conjugate? Does it affect the direction of H? No, it doesn't. It just affects the phase. Right? And this should also look familiar to you. It's 1/2 VI conjugate. Right? Where is 1/2 VI conjugate? That is the power inside your circuit. Right? The power that is supplied by the sinusoidal voltage source, or the power consumed by an RL circuit, etc., etc. So this is for your plane wave propagation. Okay? So this, and that is actually the end of our uh, lecture 10 on plane waves. Again, if you have any questions, do not hesitate to leave a comment. I will answer it as soon as I can. If you don't have, sorry, not if you don't have. So just comment your questions. And I'll see you next meeting.